Okay, Dr. Darbro here again. This is the third video on type 2 errors, beta and 1 minus beta. Also calculation of power. All right, let's switch it up a little bit. Instead of having a claim about a mean, let's have a claim about a population proportion. So let's say that just for the heck of it, that someone claims that 32% of Ohioans prefer Obamacare, or the Affordable Health Care Act. And for some reason, someone would like to test this, but they don't really prefer to perform a directional test. They don't necessarily want to know that the motivation for the test is test because they think it's higher or lower. They just want to test it. So they're going to do what's called a two-tail test. And this is standard in most tests of hypothesis. We'll test at alpha equal 0.05. All right? They go out, collect a sample. And guys, if you're testing a population proportion, you'll go out and get a sample proportion. Recall that a sample proportion is found by taking x over n. And just for the heck of it, let's say that they decided to sample 1,400 Ohioans, and 423 said that they prefer or support the Affordable Health Care Act. All right? Now, the problem, or the question, what is the probability of a type 2 error and power if the true value of P is 0.29? Now, following what we did in the previous problem, the very first thing I want to do is I want to examine the hypothesized distribution. And that would be the one with the mean or the hypothesized claim of 0.32. All right? So, and again, we're doing a two-tail test. And again, alpha 0.05. Now, so I get a little better drawing. I want to get over to a full screen. So what I'm going to do here is I'm going to center this. So you guys gotten better at drawing normal distributions? Probably have. Alright gang, right in the center is 0.32. And guys, remember we are conducting a two-tail test, which tells me I have to put part of my rejection region in the left tail. And it tells me I have to put half of my rejection region in the right tail. Alright? Now, since alpha is 0.05, I need to divide that by 2, put half here and half over in the other tail. So guys, it should make sense to you that we're going to put 2.5% of our distribution as a rejection region in the right tail and 2.5% of our rejection region in the left tail. Now, the next thing we got to do is we've got to kind of look ahead a little bit and see what true value are we making our calculations. Because if we're making a calculation based on a true value above P, then we're going to focus on this part of the distribution. If we're making a calculation based on a true P below 32 to the left, then we're going to focus on this. Well guys, clearly if you think back to what we're doing here, we're testing if P is equal to 0.29. So gang, going back to our distribution, what we're going to focus on is just this part right here. Okay? So let's make that happen. So now I'm going to kind of exaggerate this a little bit just to make a point. So we really don't care about the hypothesized distribution of 0.32 to the right because it's irrelevant to us. So what we do worry about, what we are concerned about, is the line in the sand in this tail right here. Now let's go ahead and put our other distribution in here, the one that is the true distribution, and the distribution that our, I tell you what, that's going to drive me insane there. Where the distribution is actually x, so that whole thing's going to drive me insane. Sorry guys, my ADHD is, or my OCD I guess would be kicking in here. That was just too poorly drawn for me to be able to like it. Alright, let's see if we can get a better distribution here. Alright, that's a little better. Still kind of ugly. But nevertheless, this thing is going to be centered at 0.29. Now, before we go any further and start doing a lot of calculations, let's come in here and put in blue or yellow. What area under the curve are we going to calculate for beta? Well, first of all, the calculation has to be made in this distribution because that's the true distribution. And the calculation has to be to the right of this line because the definition of a type 2 error is we have failed to reject, which would happen over here of our original distribution. So guys, it actually turns out that the value for beta, I saw this earlier, that's why I wanted this area to be a little bit better drawn, is going to be from there to there. So now what do we need to find here? Well, we need to find the line in the sand first of all for this distribution and then change it over to this distribution. Alright, so let's go for it. It should be something pretty simple to do at this stage of your statistics career. Okay? Alright, so the very first thing I want to do is I want to find the p hat that represents the line in the sand for the p equal 0.32. Okay? So let's do it. So gang, what we'll need to do here is we'll do inverse norm, 0.025, comma 0, comma 1. Now why did I use 0.025? Well guys, let's go back to the hypothesized distribution. We're looking at this area right here. We're focusing on this distribution because it's the hypothesized distribution. So we need the line in the sand that has 2.5% of the distribution to the left of it. Now you should already know that this is going to be negative 1.96 because when you have 2.5% to the left and 2.5% to the right, you have the z criticals for the 95% confidence interval. But if that it isn't clicking just yet, don't sweat it. Plug it in your calculator and you'll see you get negative 1.96. Now the next thing we need to do is we need to find p hat. But not the p hat that we got from our sample, but we need to find the p hat that represents the line in the sand. This 1.96 right here represents the line in the sand for this distribution. But we want to find a measurement that's consistent from both distributions, consistent within both distributions, and that would be a sample value. So we're going to use z equal p hat minus p over the square root of p times 1 minus p over n. Guys, remember, all of our calculations still have to be within the context of 0.32. Why? Because the negative 1.96 was in the context of 0.32. So negative 1.96 equals p hat minus 0.32. 0.32 times, if you can't take 1 minus 0.32, don't sweat it, just pick up your calculator. And guys, we have a sample size of 1400. It's kind of weird, but let me go all the way back here. Remember when I gave you all this information right over here? Never use it. The only thing we need from that is just the 1400. What I want you to realize is when you're testing a claim, you always collect a sample, even though in this context you don't use anything other than the sample size, which is equal to n. Alright, so let's make it happen, guys. We're going to have p hat. Whoa. I'm already there. So guys, first thing I'd want to do is multiply both sides by the square root of 0.32, 0.68 over 1400. So I'm going to get negative 1.96 times the square root 0.32 times 0.68 divided by 1400. And I get negative 0.0244. Now this is all going to cancel. So on the left hand side I get negative 0.02444 equals p hat minus 0.32. So guys, obviously we're going to add 0.32 to both sides. So the p hat that we get is 0.29556. Now depending on rounding, you might be off a little bit. I kept the negative 1.96 running in my calculator. When I performed inverse norm 0.025, 0, 1, I just left that value in my calculator and multiplied it times the square root of 0.32 times 0.66 or 68 divided by 1400. If you just use negative 0.96, then you're probably not going to have that exactly. Okay, gang, nevertheless, in this new distribution that we've got, now remember, here's the distribution that was in the hypothesized distribution. This is the true distribution. There was a line in the sand that gave us our rejection region from the hypothesized distribution. But what we're wanting is that right there. And we know that p hat equals 0.29556, which is consistent to both these distributions, is the line in the sand. So guys, what we need to do now is we need to find the location of the 0.29556 in this distribution. Well, that should be easy to do too, right? Because it has a mean of 0.29. Keeping consistent 1400 sample size. Alright, so let's perform that in our calculator. And when I get that, I get a z equal 0.4588. So back to our distribution here. Relative to this distribution, and I'm really making ugly, this sample proportion is 0.4588 standard errors above this mean. So guys, that means that we can take 0.4588, take the area above, and we're going to get the probability of a type 2 error. So guys, we're going to use normal CDF. Actually, that would be, if we just went to 3 places, it would be, I'm going to keep it running in my calculator, but that would be 0.459. Alright, so the answer up to E99, comma 0, comma 1, and we get a beta of 32.3%. So the probability of us failing to reject a false null is 32.3%. Our power is 67.7%. So guys, what's this tell us? We have a 0.677 probability of rejecting a false null when the true proportion is 0.29. Alright guys, that's about as hard as it gets. Hopefully we got something out of these last few videos. This might be a place where your high school teachers are really going to have to jump in and provide a little bit extra lecture. If you talk nice, maybe I can come to the high school sometime and maybe give a lecture or two. So we'll see. Alright, so guys, take care. That's the end of this video.